Hello, this is Christian Rapp, and I will be going over homework number 4. So the first problem to go over is this one about critical paths. And so critical paths are basically the slowest part of any given digital circuit. So when you're given an input, you want to see which outputs change last for you to get the correct answer. And this matters primarily because this will determine how fast your computer can run. So for instance, here you would see that it will definitely not be the first bit because this one is just a simple logical AND operation, while in other places we have carries and have to do computations based on other computations. And surprisingly, it's actually not the last bit or the most significant bit either. That is the critical bit. And you can see that here from the simulation results. So 50 nanoseconds, the input goes high. Shortly after that, the least significant bit goes high as a result. And then the bits continue to change until we get to the fourth bit changing. And in this case, the fourth bit is the slowest bit. However, it's a bit more complicated when we get to the input. This one is 1101 times 1101. And we see the input goes high again. And the least significant bit follows shortly after. And then bits continue to go up and down until we settle at our answer right around here, which is actually when the sixth bit goes low. And so it's not the seventh bit that is the critical that's the critical path in this case. All right, on to number 2. Static metric math. So we want to find VM mathematically. And so this is pretty easy, actually. We can just do VM equals Vmax. Sorry, one sec. Vmax minus Vmin over 2. And so that's just going to be equal to 6 minus 0 over 2, equal to 3 volts. And again, Vm is the point at which V out equals V in. And this is just pretty much just an approximation. There's some more exact ways to do it, but that's the easiest one. So next we want to find gain. And so gain will be the slope. So if we have this, gain will be the slope of the transfer curve at Vm. So let's start. So the equation we're going to use is gain is equal to 2 times K prime times Vm minus Vt, return on voltage, minus or times 1 over 2 lambda IDS. Great. So we see that this term depends on K prime, Vm, Vt, which we have, and lambda, but we do not have IDS, so we have to solve for that first. Because IDS is in the saturation region, we're going to use the equation IDS equals K prime over 2 times VGS minus VT squared times 1 plus lambda VDS, where lambda is the channel width modulation term. Great, and we have all the values for this equation, so we can just plug that in. What is K prime? So it's 200 micro over 2 times VGS, which because we're at VM, where input equals output, VGS will be equal to VM. Turn on is 0.5 1 plus 0.07, and then VDS will also be 3. And so this will give us a value of by 2 times 3 minus 0.5 squared times 756.25 micrograms. So now we can go back to equation for G, 2 times 200 micrograms times Vm, which is 3, Vt, which is 0.5, all over 1 times 2 times 0.07 times our new terms, 6.25 micrograms. And we get G is equal to 200 times 2.5 divided by 2 times 0.07 times that results. And we get, oops, not that. We get equal to 9.445. Great. Let me just make this smaller. Right, C, we want to find V in low. And so to do this, we are going to use the equation. VO max is equal to minus G times V in low plus VM times 1 plus G. So this is from page 81 of the slides. And so here we can just plug in numbers, or actually first we need to rearrange this equation. So it's going to be Vm times 1 plus G minus VO max all over G is equal to V in low. And that's going to equal 3 times 1 plus 9.45 minus 6 all over 9.5. And that is equal to 2.68 volts. And then we are going to want to do a similar thing for V in high. So V min is equal to minus G times V in high plus Vm times 1 plus G. Rearranging the equation, we get we get 1 plus G minus VO min all over G, and that's going to be equal to 3 times 1 plus 9.45 minus 0 over 9.45, which is equal to 3.31 volts. Great. On to the last question. So the smaller blah, blah, blah. Please keep L of both transistors equal to 10 micrometers. So the VTs of the PMOS and NMOS are equal. What WP would you need to make the TPHL and TPLH times equal for an inverter? So the process for this one is we want to have the current, because the propagation delay and T rise and T fall are related to the current through the transistor. We're going to want to set the current through the transistors equal to each other. And we're going to start, so we'll start with the current equations. So IDS is equal to K prime over 2 times WRL times VGS minus VT squared. Okay, so now we want to set IP equal to IN so that they will have the same delay. And so we're going to get KP prime over 2, WP over LP times VGS minus VT squared is equal to KN prime over 2, WN over LN times VGS minus VT squared. And that's N and that's P. But we know they're equal, and we know VGS is also going to be equal, so we can cancel these terms out. We want ln and lp to both be the same, so we can cancel those terms out. The 2's cancel out. We're left with a simple relation where wp is equal to kn prime over kp prime all times wn for this case where the VTs are equal to each other. So thank you. Have a